Airworthiness requirements. First, a few terms you need to know. TBO stands for time between overhaul. Essentially, that's how long you can run the engine before you have to take it off, disassemble it, inspect it, fix everything that's wrong, put it back together again, and hopefully the engine's pretty close to being as good as new. On jet engines, TBOs vary by how you keep track of when they're due. Some TBOs are based on how many start cycles. It might be every 2,000 start cycles you have to overhaul the engine. It might be every 6,000 hours you have to overhaul the engine. And some TBOs are based on how often you are based on how you use it. If you run it at high power settings a lot, if you're flying a Navy jet on an aircraft carrier and it's exposed to salt air quite a bit, or if you're flying it out around the desert and you're sucking in sand a lot, you might have to overhaul it more often. So those are some factors that affect how long the TBO goes. Unlike small piston engines like a 172 engine, where it's very common for normally aspirated piston engines on airplanes, that is, engines that don't have turbochargers and superchargers, 2,000 hours is a pretty common time. If you start turbocharging it or supercharging it, then you're probably going to go down to 1,500 or 1,200 hours. But on jets, it varies dramatically, so every jet's going to have a different TBO. And there is one way to get rid of TBOs, and that's to have an engine that's operated on condition. On condition means that there isn't a TBO. You never have to take it off of the airplane, send it to a shop, disassemble it, inspect everything, fix everything that's wrong, and put it back together again. You don't ever have to do that. What you do instead is just like you would if you had a TBOs. This is inspecting it at specific intervals on that engine. If it's an engine that's on condition, they're going to have little holes on the engine that you can open up, that a mechanic can open up and look inside of the engine without having to take it apart to inspect it. So you're going to have to inspect it at specific intervals, and if anything's wrong, you're going to have to fix it. But you don't ever have to specifically go, oh, well, 6,000 engine starts, now we got to take it apart. All you got to do is keep looking at the turbine blades, and if it still looks okay, then you got to keep flying. Excuse me. Of course, we all know what life-limited parts are. They're parts that, after long periods of use, due to vibration or loads on it or heat, the part is weakens, and before it weakens to the point that it's going to break, you got to take it out of the airplane and you throw it away. If it's a life-limited component, you can't fix it, you can't repair it, you can't inspect it, you can't do anything to it to make it airworthy and then stick it back in the airplane. You might be able to melt it down or scrap it, but then it's not the same part anymore. So there's not really anything you can do to it. And life-limited components, I've seen life-limited components that hit their life limits based on the number of engine cycles, like starting cycles, or on how many hours that you operate it. MTBF is mean time between failure. And this is a very common term in aviation when you start getting into larger aircraft. That is, how long can you run it on average, or actually it's the mean time. Mean means if here's 0 and here's 10,000 and it breaks halfway there, the mean time would be 5,000, not necessarily the average. In any case, I'm not going to get too much into the definition of mean versus average today. But this is when it is likely to, a certain component is likely to fail. Service bulletins and TBOs. Service bulletins are published by the manufacturer of the engine, the airframe, the propeller, the appliance, whether it's a radio, an ELT, a tire, a brake, a wheel, a hydraulic cylinder, an engine starter motor, an electrical generator, a fuel control. Service bulletins are put out by the manufacturers of all these things, and they tell you that there's something that, excuse me, might go wrong. Might go wrong, and they want you to do something about it. They might have you fix something, inspect it, replace a part in advance of something failing. But you got to understand that TBOs are recommended. And and so are service bulletins. Under FAR Part 91, you do not have to do it if you don't want to. It's a good idea, but you don't have to. However, when you're writing under FAR 121 and 135, they are mandatory, even though it may say recommended. When you're writing up your air to get approval for your air agency certificate to operate a 121 or a 135 airline, you're going to write into your air agency certificate the procedures that you're going to follow, all the service bulletins and all the recommended TBOs, even though you don't have to under Part 91. Engine modules. It's common, especially these days on newer engines, to have the engine built so different chunks or modules of the engine can be removed without having to take the engine off of the airframe. So let's just say here's our wing, and here's the cowling, and inside here we've got our duct for our bypass fan, and then of course we're going to have the rest of the engine. And if you have to take the whole engine, I guess the pylon's not very big here. You got to understand that we've got electricity. We've got electrical wiring going to the generator. We have bleed air coming off of the engine. We have fuel coming in. We have hydraulic fluid going in and going out. And we've got to connect these to all the parts on the engine, probably down here on the accessory section. So in order to actually take the whole engine and take it off of the airplane, we've got to connect and disconnect a whole bunch of things. Oh wait, the throttles, connections have to be made. So in order to take the whole engine out, the whole airplane has to sit there and do nothing for a long time, even though maybe all we need to do is replace the accessory section. Or maybe what we need to do is just replace the turbine section. So engine manufacturers have figured out ways so that you could, say, take the fan off without having to take the whole engine off. So all of these things that have to be connected to the engine don't have to be disconnected and then reconnected. And then, of course, if you only have to replace the fan, then all the rest of the engine part is just sitting around on the ground doing nothing. So you don't have to have so many engines sitting around waiting to put back into an airplane. It costs you less money. So it's very common to have engines designed in modular form so you can take parts of the engine off, big parts of the engine, big modules, and the rest of the engine still stays on the aircraft. So it does two things. It increases your uptime, which means it's also less downtime, which also means it stays in service. These are all talking about the same thing. And so, of course, you can make money on it, or if it's a corporate jet, the boss gets to fly whenever they want to go. And then the second thing it does is you have less cost for spare parts, for spare engines. You don't have to have as many spare engines lying around. You only have to have one fan, one compressor, one combustor, one turbine, maybe one exhaust, one accessory section, instead of having 2 or 3 engines lying around. So in case one comes out, you got to put another one back in. You only have to replace the part that went bad. And here's the really good part. R&R means remove and replace. Remove and replace. That's an aviation industry standard term. R&R means you took it out and you put in a different one. So you can replace that module with the engine still stuck on the aircraft. And of course, I already gave you 2 reasons why airlines like modular engines. It increases the time that the aircraft is in service, and 2, it reduces the cost of having a lot of spare parts, a lot of spare engines sitting around doing nothing that cost you money. HS stands for hot section. HSI stands for hot section inspection. I know you're used to calling it the horizontal situation indicator, but when it's referring to jet engines, a hot section inspection is referring to looking at the turbine section and the combustion section. For instance, one of the reasons why PT6, Pratt & Whitney PT6 turboprops are so popular is that I didn't draw it quite right. We'll try again. One reason why PT6s are so popular in turbine engines is that the power turbine that drives the gearbox and the propeller, it's out in the front. Here's the engine. And the airflow comes in, and it's a reverse annular through flow. Engine, reverse annular through flow engine. And guess what? The engine, if you take the cowling off of the airplane, you can literally, the engine is bolted in pieces right here. So you can take, and right here, so you can take the propeller, the gearbox, and the power turbine off, and now you can look at the turbine and you can look into the combustion section very, very easily and do a hot section by looking at all the turbines and by looking at the combustor. And it's really easy to do. The gearbox on this engine, the accessory gearbox, is on the front of the engine. So all of the parts coming in, the fuel, the electrical, the throttle control, the power lever, and the prop lever, and all that stuff is hooked to the front of the engine. So you can easily do a hot section inspection, an HS or an HSI, on a Pratt & Whitney PT6, and you don't have to disconnect hardly anything going to the engine. So that's one reason why Pratt & Whitney PT6s are so popular, is that it's really fast to do a hot section inspection. Now typically, let's just say you had 6,000 hour TBO. It might be that you have to do a hot section inspection every 3,000 hours. So that means if you get the engine and it's brand new at 3,000 hours, you don't have to do a TBO, you don't have to overhaul it, but all you have to do is a hot section inspection. And then, of course, when you hit 6,000 and you do the overhaul, you're, of course, going to do a hot section inspection at the same time. What you're looking for is cracks in the combustion liner, in the combustion case, in the rotating turbine blades, in the stationary turbine blades, and in particular, in the rotating blades, you're looking for creep. So here's the shaft, and we'll say that here is one turbine blade, and the airflow is going like this. What's going to tend to happen is that this blade is going to get pulled out due to centrifugal force, and it's going to tend to get pushed back by the gas loads, by the high velocity hitting the blade. So what tends to happen is this blade, if we look over here, this blade tends to get bent. It gets, we're going to heat this thing up, so it's going to tend to bend, and at some point, it's possible that you might have a crack. So creep is the fact that this blade is slowly going to deform, and of course it might crack, and then of course we're going to be unhappy when that turbine blade ends up breaking off. So creep is normal, but only a little tiny bit. If it gets too much, then we're going to be pretty unhappy. Cold sections are almost always made of the compressor, and nowadays, of course, since we have fans, it's also likely to include the fan if you have a turbofan. So if somebody says, oh, we had to do a cold section inspection, you know they're talking about the compressor, and if it's a turbofan, they're probably also talking about the fan. One thing that has, it's been going on for a long time, but mostly it's been manually done, is now is automatic trend and performance monitoring. That is the reason for wanting to monitor what's going on with the engine, how it's performing, and what trends are occurring, as in, is the EGT slowly rising every time you operate the engine? You have to burn a little bit more fuel to get it to have the same amount of thrust, is so that you can predict that something's going to fail, therefore fix it before it ends up failing. This will save you a lot of money. Now, it's granted it's true, if you fix it before it fails, it's very likely that the other things it'll break. Let's just say, for instance, we've got a turbine engine, and we're monitoring different parts of the engine, and we find that this turbine blade is starting to creep, and it's going to end up breaking, and not only will it break, but it'll end up flying through the turbines behind it, and so all of the stationary blades are going to get damaged, and all of the rotating blades are going to get damaged. So certainly, if we can just replace one blade, it's going to save us a lot of money because we won't have to replace all of these other blades. So that's certainly true that it saves money there, but it also keeps less downtime. And I know I keep talking about this, less downtime. That is, the airplane or the engine won't be out of service as much because it's going to be take a lot less time to replace one turbine blade. Besides, this turbine blade might hit the exhaust pipe as well. It's going to take a lot less time to take the engine out, put another one back in, whenever we want to do it. The next time the airplane comes in for maintenance, when it's already scheduled to be out of service, when it's scheduled to be down at the next inspection. If we can do it then, the airplane was going to be out of service anyway. So maybe there's no more downtime than there would have been otherwise. But if this fails, whenever it does, we're going to have to stop flying that airplane when we had planned on flying it. And if it's an airline, then we were planning on making money with that airplane when it was up. So it not only saves cost on parts, it also saves expenses by having the airplane be up or have less downtime. There are systems where you manually record it. When I was flying on B-52s in the service, every flight the co-pilot would have to, at some segment of cruise flight, write down the outside air temperature, the pressure altitude, the EGT, the fuel flow, the RPMs, oil pressure, oil temperature, all that stuff. And that would end up getting put into a computer on the ground, and someone would be looking at that going, how is this changing over time? Nowadays, there's a lot of systems out there where where the computer's automatically recording it, especially on engines that are FADEC, Full Authority Digital Electronic Control, where it's very easy for all of this data that's already being looked at by the electronic engine control, the FADEC, to be recorded and then be downloaded off of the airplane every few flights, put into a computer program, and it can actually start looking and say, hey, this is starting to change. And in the past, when this started to change, the prediction is that it's going to be this particular part that fails. So at about this time, at the next inspection, take this part out of the engine and put in a new one. So there's a lot of different things that can be recorded, whether it's automatic or manual. It might be the engine pressure ratio, the RPM of N1, N2, N3. Of course, the exhaust gas temperature is for sure going to be one of them. What the fuel flow is, how much the engine is vibrating, what the outside air temperature is, what's the pressure altitude, how fast are you going, how often are you having to put oil in the engine. If the oil consumption gets too high, maybe there's a leak in one of the bearings. And if there's anything inside of the oil contamination is tested by a specific system called SOAP. SOAP does not clean the oil or the engine. SOAP is just an abbreviation for Spectrometric Oil Analysis Program. Literally, every so often, right after you shut the engine down, you take some oil out of the oil reservoir, usually ground personnel do this, and you send it off to a lab and they burn it. As they burn it, different metals give off different light. Light, metric, measure. So they're measuring the color of the light, the spectrum of the light that's being produced when you burn the oil, and different metals inside of the oil generate different color of light, and for how long it burns is how much is in there. And they can actually predict what's going on inside of the accessory gearbox, the propeller or output shaft reduction gearbox, inside of the bearings. Anywhere the oil is going, they know what those metals are made of. So if they see a certain metal has a high concentration in the oil, they know that those parts are going to fail pretty soon. So this is a very, very common thing to do. You can even do this on a piston engine and start estimating based on how many hours it's flown and when was the last time you changed the oil, which parts are going to fail shortly or fail soon. So there's a lot of different things you can monitor to try to tell you what's going to happen to the engine in the future and fix it in advance. When we say engine washing, we're not talking about the outside of the engine, we're talking about the inside of the engine. If you fly a small turboprop as a commuter airliner in Hawaii, or you're flying a jet off of an aircraft carrier, then you're probably going to get a lot of salt sticking to the compressor blades. If you fly a small turboprop in the San Joaquin Valley of California or Los Angeles or some other big city, you're probably going to get smog particles sticking to the engine. And there could be a lot of other different things sticking to the compressor blades and the turbine blades. And of course, if you've got some nice compressor blade shape and you start getting particles stuck to it, and I'm exaggerating the size here, then the aerodynamics of that compressor blade or that turbine blade are not going to be what the engineer designed it for, and it's not going to be as efficient. So you're going to have to burn more fuel to compress the air, or the turbine blades won't be able to extract as much air as they were designed to do. So what you want to do is get rid of all these things sticking to the blades. Well, a water wash is typically done when the engine is not running. You typically motor the engine and spray water. There's usually some gizmo that sprays it just right into the engine, and that is pretty good at getting rid of salt and a little bit of smog and maybe a little bit of the particulates. However, it won't get rid of everything. So there's literally, they grind up walnut shells or peach pits. I'm not making this up. And they spray it in. It's like turning a vacuum cleaner on backwards, and it sucks it up. These small particles, about the size of grains of sand, maybe a little smaller. It's not quite dust. And you blow it into the engine while the engine is running. And of course, if the engine's running, the velocity of the air is pretty fast, even at idle. Even at idle, we're talking about 100 or 200 knots. So peach pits or walnut shells, we're talking already ground up, not full size, are going to hit the blades and knock off whatever is stuck to the blades. And hopefully some of them will get through the turbine section and go out the engine. And if they don't, they'll get burned up anyway, because they're made out of organic material, almost like wood. In any case, you don't want to do this too often because you can wear down the metal of the blades, but you do want to do it often enough so that you get rid of this accumulation so the engine will run like it was supposed to. If you measured the EGT and fuel flow for a particular thrust, you'd find that the EGT goes down and the fuel flow goes down because the engine is more efficient. Essentially, that means then that since the EGT is lower, then that's going to increase your service life. And fuel flow lower is going to mean that TSFC is going to go down. So these are both wonderful things. We burn less fuel for the same amount of thrust, yay! And the engine lasts longer without us having to replace components, or when we do hit overhaul time, we won't have to replace as many parts because they're lasting longer because we didn't expose them to as high of a temperature. If you want to build an engine and bolt it onto certified aircraft in the United States, you have to look up and follow FAR 33. Just like FAR 25 is the FAR if you want to build a transport category jet and then sell it in the United States, you have to build it just like FAR 25 says. If you want to build engines to put on anything that's a certified airplane or a helicopter or blimp, then it's got to be built in accordance with FAR 33. Okay. I looked it up. FAR Part 1. A large aircraft means that it weighs more than 12,500 pounds if it's at its maximum certificated weight. So just because you don't fill it up to its max certificated weight doesn't mean that it's not a large aircraft. It's either a large aircraft or it's not. So that means it's a small aircraft if it's less than if it's at or less than 12,500 pounds. So if you build an aircraft and you make its maximum certificated weight to be 12,500 pounds, it's a small aircraft because it has to be more than 12,500 at its maximum certificated takeoff weight, and then it's a large aircraft. If you look towards the back of FAR Part 91, you'll find things that have to do with maintenance, like the FAR 200s, 300s, 400s. It talks about when to do 100 hours, annuals, progressive inspections, when you have to get the ELT inspected, stuff like that. In the 500s, the 91.500s, it talks about what do you have to do if it's a large airplane. That means it's greater than 12,500 pounds max gross takeoff weight. Whether or not you're at it or not doesn't matter. Or if it's powered by a turbine and it's a multi-engine airplane. So if it's above 12.5 max gross takeoff weight, even if it's a piston-powered flying machine, it's a large airplane. But if it's got a turbine engine in it and there's 2 engines or more, now we have these additional operating rules, even when we're operating under Part 91. Now it actually says in there that this is not for airplanes operated under 121 or 135. If you have an operation under 121 or 135, scheduled air carriers or air taxi operators, or non-scheduled air carriers is another way to describe Part 135, then you're going to have all a completely different, not a completely different set, but you're going to have all these rules and a whole bunch more. So this rule in Part 91 here in the 501 to 535 is only talking about operations of large airplanes or turbine-powered multi-engine airplanes operated under Part 91. It mandates the use of a checklist. I know that sounds pretty funny, but if you flew an airplane that was built before 1979, it didn't have an approved flight manual, it had a pilot operating handbook, and you didn't actually have to use a checklist. Now it requires you to use a checklist no matter when the airplane was built. It has certain requirements for survival and safe emergency equipment. And actually, you have to start briefing the passengers. If you look at really all you have to do passengers under Part 91 on little airplanes, small aircraft, is to make them put on their seatbelt. Now, granted, we may tell them a nice little briefing so they'll be more comfortable and be safer, but now it's absolutely mandatory to brief the passengers. There are certain conditions about if you're going to fly through icing. There's certain policy rules in this part of FAR 91 that tells you requirements about stowing cargo and stowing food. And if the airplane has a second in command, it tells you about the requirements for what you have to have if you're that second in command pilot. Typically, you have to be rated in the airplane and have 3 takeoffs and landings within the last 90 days. You don't have to have a type rating. Oh, just by the way, if the airplane weighs more than 12,500 pounds, then you're going to have a type rating for it. Okay, rules of thumb. How much does the engine cost? Well, if the engine is producing, if it's a turbojet, a turbofan, and it's producing 500 pounds of thrust, just multiply this by 200. Or multiply the 50,000 by 200. 2 times 5 is 10. Whoops. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. $10 million. Let's see if I did it right. Woohoo! Yeah, $10 million. So I know what a factor here. If you take the thrust of a turbofan and multiply it by 200, you're going to get the approximate. This is a very approximate number. For instance, if you take the GE90, the latest version of it produces 115,000 pounds of thrust. If you multiply it by 200, you end up with $23 million. I'm not making this number up. That's how much that engine would cost. So that's probably right now the most expensive jet engine you can buy to put on an airplane. Now, equivalent shaft horsepower, you probably don't remember, but equivalent shaft horsepower is the gross thrust over 2.5. So if we divide it by 2.5, we're going to end up having to multiply it by 2.5. So 200 times 2.5 is 500. So if we multiply the equivalent shaft horsepower, or if it's just a turbo shaft engine, we're going to have shaft horsepower. If we multiply it times 500, in this case, we're going to get $250,000. So a very small turboprop might be $250,000. If you look at the Pratt & Whitney PT6s on a Beech 1900, those are probably, and I'm guessing probably, have 1,000 equivalent shaft horsepower. If we multiply that by 500, we're going to get $500,000. So it's probably very likely that those engines on those PT6s on a Beech 1900 cost about $500,000 a piece. Yep, there we go. And overhaul cost. Overhauling jet engines is mostly parts. It's about, of that amount of money, it's probably 70 to 80% is parts. And if you took a $10 million engine and it's coming in for overhaul, you multiply it by 0.6, you're looking at $6 million. So that PT6 out there on a Beach 1900 times 0.6 is going to be about $300,000 to overhaul it. So if you find the cost of the engine new, you multiply it by a little more than half, that's the approximate cost of overhauling it. Now this is even more approximate than these other factors because it depends on how you operated the engine, how old it was, how new it is. So that's going to vary quite a bit. Okay, you want to go out to the airplane, and you go out to the airplane, you're pre-flighting it, and the cigarette lighter's broken. You still want to go flying. You can use FAR 91, it's in the 200s, and you can use it, this part in the FAR, to legally fly an airplane even though something is broken. I call it my 4 checks plus 3 actions found in FAR Part 91. You have to check 4 things, and then you have to do 3 things. And then if all of these things are good, you can go fly the airplane. You've heard of this before, so I'm going to go over it pretty fast. First, you got to make sure it's not required by FAR Part 91. Is it day VFR? You don't have to have a gyro. If you're above flight level 240, you got to have a DME. If you're operating the aircraft for hire under Part 91, you have to have an operational landing light. So there's several places in FAR 91 where you're going to have to look to see if it's required. You're also going to have to look in the approved flight manual. In the back of the approved flight manual, the vast majority of the time, there's a list of components that have to be on the airplane and working under certain conditions. You have to comply with it as well. You're going to need to check to see if this component is required by an airworthiness directive. Now, this is extremely uncommon, but what I find rather interesting is that if you have a turbine-powered aircraft, and you have a NiCad battery, there's actually an AD about a temperature indicating system for the pilot. And there's an AD that says every single aircraft that has a NiCad battery has to have a temperature gauge for the NiCad battery, because NiCad batteries can have a thermal runaway and get too hot. But most of the time, this is the least likely one that you're going to check and have something be a problem. You also have to check and make sure that if this component is inoperative for this flight, it's not going to be a hazard to the aircraft. Like if you're flying day VFR from Prescott to Kingman, you think it's okay not to have a gyro. I think it's okay if it's day VFR to Kingman that you don't have a directional gyro. It would not be a hazard. So if you check all these things and they're not required and it doesn't make it hazardous to operate the aircraft, then you either have to deactivate the component or you have to remove it. Unfortunately, this is a maintenance action, and so is placarding it. You have to put a placard next to or on top of it, and it has to say inoperative. And I'm not talking a yellow sticky. It's got to be something permanent. So that way, if somebody else operates the airplane tomorrow and they don't pre-flight it as well as you, they'll easily see this placard saying that it's inoperative. Like if it's the directional gyro and they're going to go fly IFR, the gyro is required by FAR, and I'm sure it's going to be required by the approved flight manual, and one might consider that not having a directional gyro flying IFR would be hazardous. You definitely want other people to know, so that's why you're going to have to put a placard that you deactivated the component or you removed it, is so that they'll know the next time they fly the airplane that something's wrong with the airplane and they need to pay attention to it. And since both of these 2 items are maintenance, you have to write it up. An airplane is unairworthy when you do maintenance until you record what you did in the maintenance records. Now, the problem with this is most of the time this takes a mechanic to do this, since your privileges under Part 91 as a pilot don't have very many things that you can fix. So most of the time, in order to do this, you're going to have a mechanic come out and deactivate or remove it, placard it, and then write the maintenance in. Now, there's another way to be able to fly the aircraft when something's broken and be legal, moral, and ethical. And that's having an MEL. I'm not talking multi-engine land. I'm talking minimum equipment list. Minimum equipment list. Minimum equipment list is also described in FAR Part 91 in the 200s. When you first get an airplane brand new out of the factory, the manufacturer will come out with a master minimum equipment list, an MMEL. But it only has the things on it that the manufacturer installed. Let's just say that it's a a Lear 65. That's a big old honking $30 or $40 million business jet, and it comes out of the factory and it's green. They haven't even put the paint job on it. It just barely has minimum flight instruments and radios. They fly it to some place where they're going to put the interior on it and put a paint job on it, and they install a blender and a DVD player and a computer and a hot tub and a vibrating bed and another blender, and they install all kinds, a gold-plated toilet seat. They install all kinds of other stuff on it. So this master minimum equipment list doesn't have everything on it. So what you're going to do as soon as you put all that stuff in the airplane, have that all installed, you're going to write up an MEL, a proposed MEL. You're going to write up a proposed MEL, and you're going to send it to the local FAA office, the FSDO, and they're going to look at it, and you're going to write on it, if the DVD player is in op, you're going to say that day VFR, night VFR, or IFR, if it's busted, it's okay to fly. You're going to put everything on the aircraft that you installed, the VCR, the DVD, the vibrating bed, everything that you put into the, if the toilet doesn't flush, it's still okay to go flying. You're going to write up in there everything else that's on the airplane, in addition to everything that was on the master minimum equipment list. So now you get it approved. When you get it approved, then they are going to give you a letter of authorization, and you're going to keep that in the airplane in the same binder as the minimum equipment list. Now that's what it's going to be called, the minimum equipment list for that one particular aircraft. When you're writing it up, you're going to take into account anything that it says you got to do in FAR, anything that's in the approved flight manual. You're going to check any ADs that might apply to the airplane. You're going to make sure that it's not hazardous. And you're going to take all this stuff into account when you write that MEL up, and the FAA is going to approve it. So now you're going to keep the letter of authorization, and you're going to keep the minimum equipment list on board the aircraft. When you go out to the airplane and you pre-flight it, anything that's busted, you're going to write it up. That piece of paper that you write it up on is part of the maintenance records. You're also going to look at everything else that everybody else wrote up. See, part of an MEL is it's going to tell you what you have to do in order to go flying, and it may not say you have to placard it. So that's why you're going to write it down, and that's why everybody else is going to write it down. So there's in the aircraft, as part of the maintenance records, is what's broken on the airplane, so everybody that flies the airplane can now know what's wrong. So now you've got a list of the stuff that you find is inoperative, the stuff that everybody else found is inoperative, and you're going to read the MEL and see what does it say you can do. If it's single pilot and there's a directional gyro on the co-pilot side that's busted, it's probably going to say you can go flying even IFR because you don't need to look at it. If the DVD player is broken, I think it's going to say it's okay to go flying. Also, if it has an O, then it tells you that the operator can take care of it. That means the pilots. If it's got an M, that means you need maintenance. Essentially, you got to have a mechanic come out and take care of it. These four things right here are the four things you're going to have to do. If an airplane has a minimum equipment list approved for the aircraft, you have to follow it. And you're going to have to be legal, moral, and ethical, make sure that the letter of authorization and the MEL is on board the aircraft. Make sure that you write down anything that you find wrong. Make sure that you look at the list of other things that have been found wrong before you got there. And then you have to follow the MEL limitations, restrictions, whatever it says you can or cannot do, you got to do it. I have an example here of a Boeing 777 minimum equipment list. I know it's probably really small and hard to read, but right here it says if the engine fuel filter bypass warning systems, it says there's 2 installed and you got to have one that works. And M right here says maintenance has to do something. So 1 may be inoperative provided fuel, blah, 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 blah. So it's a little bit lower. Whoops, went too far. A little bit lower. Wow, this one's pretty rough. Here it says maintenance, M, and then it lists all these steps that a mechanic is going to have to take in order for you to be able to fly the airplane. However, whoops, I got another one. Here's a different one. Here's for the electronic engine controls, EEC, normal mode. If that's busted, there's 2 on board the airplane. 0 of them have to work if you want to get dispatched, if you want to go flying. And the remarks is O. O means the operator. So it says norm mode may be inoperative provided both engines are operated in the alternate mode, and dispatching with an engine anti-ice valve inoperative is not open, is not permitted, and the low pressure turbine case airflow systems on both engines have to be operating normally. And of course it says right here you have to note notification dispatch is required. So if it says O, then that means the pilots can take care of it. And if it says M, then that means maintenance is going to have to take care of it. You're going to have a mechanic come out and help you with it. And they're going to have to do something. Special flight permit is the third different way that you can legally fly an airplane even though something's broken. The vernacular in aviation for special flight permit is ferry permit. They mean the same thing. It means you're going to ferry the airplane to some place where you're going to get maintenance. The vast majority of the time, if you want to get a special flight permit, the FAA is only going to let you do it if you are flying the aircraft somewhere to get maintenance done. Typically, to get maintenance done. They're typically also going to say you have to fly day VFR, and they're also going to say that required crew members only. You won't be able to take any passengers with you. They're not going to give you a ferry permit so you can take your friends for a ride. They're not going to give you a ferry permit so you can go to a party. They're only typically going to do it so you can go to the place because you can't get that maintenance done at the airport where you're at. Okay. Also in FAR Part 91, back in the 200s, it says if it's a turbine-powered airplane, so it could be a Piper Malibu or a Piper Meridian that's got a Pratt & Whitney PT6 out in the front. It says you can never ever use that 4 checks and 3 actions method from FAR 91, which means that you're going to want to get an MEL. And of course you can use the MEL, but let's say that the airplane is brand new and you haven't gotten the MEL done yet, and the DVD player breaks. Even though it's not a safety of flight item, you can't use the 4 checks and 3 actions methods and go, well, it's not required by an AD, the FARs don't require it, blah, 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 it won't be hazardous, we'll mark it inoperative, we'll deactivate it, and we'll get to go fly. Nope, sorry. If it's a turbine-powered airplane, you can't use this system under Part 91, which would mean that if anything on the airplane broke at all, if there's no MEL, if anything broke on the airplane at all, you're grounded. You can't fly. So guess what people are going to do who buy turbine-powered airplanes? The very first thing they're going to do is they're going to get their MEL approved immediately, and they're going to write up all the little things on the airplane that might possibly break so that they can fly the airplane without being stuck somewhere. However, interestingly enough, this 4 checks and 3 steps, 3 actions out of FAR 91 can be used on turbine helicopters. Jet engines are constantly evolving to be better and better and better. Jet engines, if you look at the development of compression ratios of the compressor, that is the ratio of the pressure coming into the compressor versus leaving the compressor going into the combustion chamber, that's getting higher and higher and higher. The why is because the higher the compression ratio equals the lower the TSFC. And how do you do it? By having more and more stages of axial compression. If you look at jet engines, the newer the engine, the more stages of axial compression there are. And of course we'll have higher pressures, and that'll give us lower TSFCs. We've already covered in a lecture about having increased turbine temperatures. If we have increased turbine temperatures, then that means we need less cooling air. If we need less cooling air, we can have a smaller compressor. If we have a smaller compressor, then the energy extracted by the turbines, instead of driving the compressor, that fuel energy can be used to drive a fan, a prop, or an output shaft and give us more thrust or more shaft horsepower. So how do you have increased turbine temperatures? By allowing turbine sections to withstand higher temperatures. Make them out of materials that can withstand higher temperatures, and now you don't need so much cooling air. Greater use of full authority digital electronic controls. Why? The two reasons why FADECs are so great is, one is they're more reliable than mechanical fuel controls, and secondly, they're more fuel efficient than mechanical fuel controls, since they're more accurate. Higher bypass ratios. Why do we want to have higher bypass ratios? Because that's going to give us lower TSFC. How does it give us lower TSFC? Because we accelerate a small mass, and we only accelerate at a small amount, and increasing the mass doesn't take as much extra fuel as increasing the velocity does. So if we have a higher and higher bypass ratio, we'll have a lower and a lower TSFC. And sure enough, the Gen X engine that GE's making for the 787 has, I think it's a bypass ratio of 11:1. It's a really huge bypass ratio. Now, what you could do on turbo fans is have that fan out in the front. You could have it have variable blade pitch, just like a propeller does. And although that would improve your TSFC, I'm telling you that it's not going to happen, because such a small percentage of the time you're going to climb, you're going to cruise, and you're going to descend, and you're going to design the engine blade pitch on the fan to work really, really well at cruise, and this amount of time for climb and this amount of time for descent, you're going to say that it's not worth it, because if we had variable blade pitch, then we'd have to have a huge blade pitch mechanism. It would be less reliable because it could break, it's going to weigh more, and that's going to tend to offset the fuel savings in pounds, and it's going to be, let's see, weight. Oh, and it's going to cost more. It'll cost more to do it. So none of the engine manufacturers have ever built a mass-produced variable pitch fan blade. They're sticking with these other areas to increase TSFC. And of course, computerized, airborne, I guess automatic and airborne engine condition monitoring, trend monitoring, that's happening more and more and more, not just on the engine. For instance, on helicopters, they monitor the vibration of the rotor blades and on the transmissions so they can predict failures, not just on the engine. So that is occurring more and more and more as well. If you have any questions about airworthiness requirements, you know how to get hold of me. If you have any suggestions on how to do this lecture better, let me know about those suggestions as well. Thank you.